how to compute sensitivities. I will explain to you a very well-known method from optimization, the so-called adjoint method, but it's well-known in optimization, not so well-known in other fields. So how to actually compute sensitivities in many practical applications. So since we deal with derivatives, not randomness, I will write everything in small cap variables. So derivatives and not randomness. So for now, z, so little z instead of capital Z for parameters. So we've seen in the last section how statistical quantities can be interpreted. And recall our definition of sensitivities. So S transpose, so S is the gradient, but if we write it as a Jacobian, it's the transpose. So it's the derivative of the reduced cost functional with respect to the input variables, which means it's this dr of u of z again with respect to z. And well, if I want to compute this derivative, it's a chain rule derivative. So I have actually the outer derivative of r of u of z times the inner derivative of u of z. Yeah, where again z is now, and that's not even an impulsive notation, a vector in RD input variables. All right, that's easy enough. Yeah, so and if I look at these derivatives, the first one is easy to compute, right? So I have a quantity of interest which I compute from u, for example, the expected value of u. So this one is actually simple to compute. What's interesting is in this formula, I require the derivative of the output, solution u, with respect to the input. But the input to output relation is, that's our assumption, only implicitly given. Yeah, and in order to get this, I need to differentiate the problem. Yeah, so to get this derivative, u of z, we need to differentiate the implicit relationship we have. So the problem, which is, I'm writing it like this, so 0 is e of u of z, comma z. Yeah, so we assume that we only have an implicit relationship between the input z and the output u, and this I've written already as a function of z, yeah, because we assume that we plug in the solution. Now, that should remind you of something you do in your first year of calculus, namely the implicit function theorem, and that's essentially what we do here. So how to get the derivative? Well, I just differentiate this problem. So I still have 0 on the left-hand side if I differentiate, and now I differentiate everything with respect to z, and I have chain rule again. So I have the z in the two arguments. So I first need d over du, e of u of z, comma z, times the inner derivative, d over dz, u of z. And then I have the derivative with respect to the second argument. So plus a d over dz, e of u of z, comma z. And in this case, this d over dz here means I differentiate with respect to the second argument. And now I want to add something to this. So I'm taking this formula up here. So if I now look at the sizes of this thing, it's always good if you do multidimensional calculus to check what the sizes are. So let me write it down first. So in the case that all quantities are vectors, So I'm assuming Z is a d-dimensional vector. I now introduce something new. I'm assuming that U of Z is an Rn. So my solution has n components, and I'm assuming that I'm interested in Q quantities of interest. Yeah. Then what's the assumption? Then E of U and Z. So if I compute this, must also be in Rn because we assume unique solvability of this thing. Yeah. So we're assuming that the solution has n components. If I want unique solvability, then for the n components that I want to compute, then typically I should have n conditions. Yeah. So E of U and Z is a vector in Rn. And then now we can do what I wanted to do, namely look at the sizes of these quantities. So if E is in Rn and U is in Rn, this one is an n by n matrix. Then d over dz U of Z, I'm gonna write that here. So Z is d components, and we have now an n by d matrix. And finally, this one is n components, so n equations, and d unknowns. So I have an n by d matrix. And you also see that this is an n by n matrix times an n by d matrix. That gives us an n by d matrix, so the dimensions fit. All right, so that's kind of the standard assumption. And now we have the sizes of the objects in this equality. And if you remember the implicit function theorem, what you do is you make an assumption, namely that this object here, the Jacobian, is invertible, because then we can compute what we want. Namely, remember, we are interested in this one to put it into this formula here. So we assume, unique solvability. That implies that, or well, that's kind of equivalent from the implicit function theorem under the conditions stated there, that the Jacobian is invertible. Yeah, so we assume that E of U and Z equals 0 is uniquely solvable for U. And well, I've written it like this even more. So look at the implicit function theorem. That's all we're using here. We assume that this is also locally invertible, and that's related to the Jacobian being invertible. Yeah, and we assume this because then we can compute the derivative of the output of the solution with respect to the input. Yeah, that we can write this here d over dz U of Z. And well, remember we have this formula here. So here, this is the formula. So I'm inverting this one here, and I bring this one to the other side. So what I have is that this is minus d over du, E of U of Z, comma Z. This one I'm inverting, and I'm applying it to the Z derivative of E. Yeah. All right, and what does this mean actually? So this means, more precisely, this inverse matrix actually means that we need to solve a linear system of equations. the following linear system of equations. Well, where I put everything back. So here is the matrix E of u of z comma z times d over dz u of z equals minus d over dz e of u of z comma z. That's enough brackets. So again, so this would be matrix, vector, and right-hand side. And we need to solve it for the vector, yeah, for this one here. D over dz u of z. Yeah, and it's a system, the size of the solution. So it's an n by n system. And it's not just one system of equations. It's actually d linear systems that we need to solve, because that actually is wrong. That actually is a matrix. Yeah, so this is n by n, this is n by d, and the right-hand side is also n by d. So it's actually d systems of the size n by n each. D systems of size n by n. And that's going to be important. And finally, once I have done this, I have a formula for the sensitivities. So then the sensitivity vector is given like this. So we have d over du r of u of z. And now comes the formal solution, again written with the inverse matrix. So here's the inverse matrix, and here is d over dz e of u of z comma z. And I think I'm missing a minus sign here. So all of this should have a minus sign in front. All right. Now comes the trick, actually. So what I have to do is I have to solve d systems of n by n each. And remember, we assumed that d, the dimension of the input or the number of input variables, is large. So I need to do something if this is large. And the trick is quite simple. It's called the adjoint method. And on this level, I can explain it easily. We just consider the transpose of this equation. Yeah, so I'm putting a transpose on everything. So I'm writing S. And with the transpose, the order changes. So it's a d over dz e of u of z comma z transpose. Then the transpose of the inverse, which is actually the inverse of the transpose. So that interchanges if I take the transpose of the inverse or the inverse of the transpose. And then finally, I have this term here, the r of u of z, and also transpose. And now I can write again what sizes they have. So this is now a d times n object. This one here is still an n by n matrix. And this here is an object that's n times q, yeah, because we have cube quantities of interest. And now I can interpret this differently, namely now the inverse here acts on this one. So this is now the equations that I need to solve. So now we need to solve linear systems of this form. Where this one is the matrix and this one here is the right-hand side, also with a transpose. And we can count how many we are. So in this formulation, we solve Q linear systems of size n by n. And well, it now depends which formulation you want to use if Q or D is bigger. But typically we have 2, 3, 4 quantities of interest. Yeah, I mean, the expected values of variance maybe, but we have tons and tons of input parameters D. So in most cases where you do practical uncertainty quantification, going to the adjoint method, namely considering simply the transpose of the equation that I've written down, solving now linear systems that have this here as the right-hand side, namely the functional, taken the derivative of the functional, rather than apply to the derivative of the equation itself. So that gives us only Q systems that we need to solve, rather than D systems we can solve. It looks simple enough, this trick, and it is, and we will see how to apply this in practice.